Hello everyone. This lesson is errors and uncertainties. Loosely speaking, an error is something that goes wrong in an experiment, and an uncertainty is the size of an error. Physics is an experimental science, which is to say, a science based on measurements. So we have experimenters performing experiments to test the predictions of a theory or for some other reason. And we know that no measurement will ever be completely accurate. There are a whole bunch of things that go on inside a practical that mean that no two readings are ever going to be exactly the same. There are things that contribute to this called errors, and all results must be presented with their uncertainty, and we'll talk about uncertainties in a bit, but they're effectively the size of the error. Now, errors come in two main flavors: systematic and random. Systematic errors. A systematic error biases measurements in the same direction and by the same size, by the same amount. A classic example of this is zero error, which we'll talk about a little bit more in a minute. So let's have a look at this ammeter. The ammeter in the picture it's not connected to anything. There's nothing plugged into it, as you can see. But the needle on the ammeter is reading 0.2 amps, even when there's nothing plugged in. So if you were to drive a current of 1 amp through this, it would actually read 1.2. So all the values you measure would be too big by the amount that it's offset by, 0.2 amps. Random errors, on the other hand, cause a spread of values about the real value when measurements are repeated. They're unbiased in any direction and are of random size. And if you average many values with a random error, you should end up with a more accurate estimate of the result. So let's look at that in a little bit more detail. Here we have two sets of measurements, and we're representing them as rounds fired into a target, for instance. So this set of measurements on the left, you can see that their average is here, and they're all scattered by a small amount from their average. These ones, their average is roughly in the middle, but they're scattered by quite a lot. So the scatter is the random error. So these ones here, the ones on the right, have a large random error, and these ones, the ones on the left, have a small random error. You can tell if something has a systematic error or not if all of the measurements are displaced by the same amount in the same direction. So all of these results have been displaced from here to here. So there is a large systematic error in the experiment on the left. Here the average of all these results is in the middle. So this would be a small systematic error, or possibly no systematic error. So let's have a look at what the effect of averaging is. Let's say you took one data point and it was this one for your first data point for this one. Now this isn't far off the average, although it is quite a way off the true value. If you took more data points for this one, your average would get closer and closer to the middle. So you would improve your confidence in this result because you see lots of them happening to be in the same area, but your result would not be accurate. For these ones, let's say these two were the first data points you took, and the average would be in the middle. You can see straight away that the more data points you have for this experiment, the more the average migrates to the center. And putting more measurements in this experiment with a small systematic error, will improve your estimate of the result, it'll give you a more accurate estimate. Accuracy and precision. So we can say an experiment is accurate if the systematic error is small, which means that the measured value is very close to the accepted value. Measurement is precise if its random uncertainty is small. So the repeated readings are very close to each other, which means we can have 4 different cases. We can have this one. These points are well scattered, so this is not precise. And the average is not nicely in the middle, so this is also not accurate. So accurate if the average sits nice and close to the true value. Precision if the random uncertainty, the scatter, is small. So this one has a small scatter and they're sitting nicely. The average is about here, which is very nearly the true value, so this is both accurate and precise. This one has a small scatter, but the average is well off the true value, so this is accurate. No, it's not. It's precise, but it's not accurate. This one, there's a large scatter, but the average is quite close to the middle, so this would be accurate, but not precise. Graphs are a really good way of detecting systematic error, and they're also a nice way of seeing random error. So if we were dealing with the perfect experiment and we have 2 quantities which we're measuring, and these are the perfect results here. They sit nicely on the line and it's a nice straight line through the origin, so maybe this is current and voltage for an ohmic resistor. Now, let's have a look at these little cross points. These have random error, so they have random error but no systematic error, so the points are scattered off the line. You'll see they're not scattered alternately, one up, one down, one up, one down. The perfect results are a line of best fit through these data points with a random error. Now if we look at the little triangles, we can see that they follow the exact same trend, but the results are all shifted in the same direction by the same amount. So we get this nice straight line still, and it's the same gradient just with an offset, with an intercept. So if you see an intercept where you didn't expect there to be an intercept, or rather a non-zero intercept where you didn't expect there to be a non-zero intercept, then this is a really good indication of a systematic error. One of the major kinds of error is parallax error, which is the error caused by the experimenter's eyes not being level with the measurement they're making. And this gets worse if the scale is not right up close against the thing you're measuring. So let's have a look at our 2 examples. On the right is a picture of a measuring cylinder, and let's say the experimenter's eyes are nice and level with the bottom of the meniscus, we get the true value. However, if your head is slightly above, you'll end up with the bottom of the meniscus looking like it's at a different position on the scale, and the same if your head is too low. Because the measurement you get depends very closely on where your head is, then this is a random error, because your head might be slightly above or slightly below, different every time. Now, a way you can improve this is by getting your head closer to the meniscus. It means that there's less room for wiggle, if you were. There's less room for maneuver. Your head can be in fewer positions and still have you think you're looking level at the bottom of the meniscus. This is an analog scale. There's a needle here against some analog scale, and the orientation that we're looking at makes it look like we're reading 76 something, let's say amps. That's quite a lot. Never mind. So 76, whatever the units on this scale are. But you can see there's a shadow here. So if you looked at this scale from a different position, like the position of the light source, if you looked at the scale from the position of the light source, you would see that it's reading 78, whatever units on this scale. So you've got to have your head nice and lined up with the needle on the scale. So parallax errors, errors due to the fact that the experimenter's eyes aren't level with the measurement they're taking. And they're random errors because they depend on the position of your head. Zero errors are errors caused by the measuring device not being properly set to 0. The results are either going to be too large or too small by the same amount. So this is an example of a systematic error. So here's an ammeter, nothing plugged in, just like the last time, and we're reading minus 0.2 amps. So if you were to put a current in, it would be too small by 0.2 amps always. Here is a ruler measuring the depth of water in a beaker. Well, you can see that the 0 mark for the ruler doesn't line up with the base of the ruler. So you put this in, you put water in here, and actually it's measuring a smaller depth than what's actually there. So let's say this was 5 millimeters to the end of the ruler. Whatever depth we measure, we need to add 5 millimeters in order to get the true depth. So all of these measurements on here will be offset by the same amount. So this is a systematic error. You can end up with errors due to miscalibration of devices. And a way to check if you have a miscalibrated device is to have a number of them measuring the same thing. In the example here, we have a number of thermometers in the same water. This doesn't tell you which is miscalibrated, but it does show that there's a discrepancy. This sort of depends on what kind of miscalibration you've got. If the results are out by the same amount in the same direction, it's a systematic error, otherwise it's a random error. Errors due to human reaction time. Human reaction time is a few tenths of a second, which is to say there's usually a delay between an experimenter observing an event and reacting to it, let's say using their timer. These are random and not systematic uncertainties, as we don't know the length of the delay. The length of the delay might be different depending on a whole bunch of parameters, like if you're expecting it, if you're feeling sleepy, if you're anticipating. So because these are not systematic, these are random errors that will be of random sizes and potentially in different directions. And since they're random, they won't necessarily cancel out when starting and stopping a stop clock. If they were, if you started a stop clock 0.1 seconds slow and then you stopped it 0.1 seconds slow, that would cancel out. But these are random, not systematic uncertainties, so we can't be sure of that. There are various ways of reducing error due to human reaction time. The simplest being ready, steady, go, counting in before a measurement. Analog and digital devices all have errors built into them. So here's an example of a voltmeter, and here's a digital voltmeter, and they're reading the same voltage. So when you're reading an analog device, you're rounding whatever you're reading to half the smallest division on the scale. So if we were to zoom in here, we would see this is at 2.4 and a bit. Sorry, 2.4 and a bit, because it's halfway between the 4 and the 5 markers. So we'll probably say 2.45 volts if we're reading off of this one because we have to round to the smallest division. And because we're rounding, that's a random error in the measurement. It's not going to be offset by the same amount every time. You might naively think that readings on a digital device will be more precise. But that's not exactly true. Let's have a look at this one. So the readings on this device can only be read to the smallest shown number. So what's happening in order to show that smallest number? Well, it's rounding in the same way that this was, only it's rounding to this number here as opposed to half the scale. So we've got quantization errors, the results are rounded, and you won't run into this one probably, but there's a thing called sampling frequency. So if it's not measuring the result quickly enough and the result is changing very quickly, you might get a result which is different than the true one. Quantifying errors. An error, we know, is something that causes a deviation of a reading from the true value. And we want to know how big those are. An estimate of the size of an error is called an uncertainty. And in science, we always have to express our measurements alongside their uncertainties because that's how we compare measurements to other measurements, and we'll talk about that later. The uncertainty says that the true value can be expected to be anywhere in the specified region. Let's have an example. So let's say we've got a voltmeter and it read 2.4 volts, but it was a digital voltmeter that was reading down to the smallest thing it could read on it is 0.1 volts. So actually, we expect the true value could be anywhere between 2.3 volts and 2.5 volts, and rounded in. So we can express that as 2.4 plus or minus 0.1 volts. This plus or minus thing is what we call an absolute uncertainty. It's a number with the same unit and you can write it as plus or minus. So we give it the symbol delta something. So that triangle there is the Greek letter delta. So if we had our measurement as x, its absolute uncertainty would be delta x. So altogether that would be x plus or minus delta x. So in this case the value is 2.4 volts and its absolute uncertainty is 0.1 volts. We can also calculate percentage and fractional uncertainties. So the fractional uncertainty is how big the absolute uncertainty is as a fraction of the value. So that's delta x over x. The percentage uncertainty is that thing times 100%. I quite like percentage uncertainties because they're more human readable. So as an example, our 2.4 plus or minus 0.1 volts, the value is 2.4 volts, the absolute uncertainty is 0.1 volts, the fractional uncertainty is 0.1 over 2.4, which is 0.04. You will note I've not left the unit off accidentally. It's not got a unit on purpose. It's because we divided something with volts by something with volts. The percentage uncertainty would be 0.04 times 100%, so that's 4%. Percentage uncertainties are quite nice because they show us what kind of level of uncertainty we're dealing with. Now in high school physics labs we're normally quite happy if we've got percentage uncertainties of less than 10%, and we're very happy if we've got them less than 5%. Resolution. Resolution is how well you can read a device. So it's the uncertainty associated with the experimenter reading a device. It's called the resolution. The resolution of a measuring device provides its own reading error. A digital scale we can only read down to the smallest shown thing. So the uncertainty on a digital scale is plus or minus the smallest scale division, the smallest thing you can read. On analog scales, you can see between the smallest scale division, so we can say whether it's a half, plus or minus a half the smallest scale division. Just beware that often you take multiple measurements, such as starting or stopping a stopwatch, or lining both ends of an object up with a ruler, so we have to combine those uncertainties, and we'll show you how to do that later. So here's a stop clock. This is a digital stop clock, and so the smallest number we can read would be 000.01 seconds. So the resolution, the uncertainty on this device due to its reading error, would be 0.01 seconds. So the reading on this stop clock you could quote it as 3.43 plus or minus 0.01 seconds. Let's have a look at a ruler. Now this ruler has markings every 2 millimeters. Let's say it's 2 millimeters. So this would be 23.3 centimeters plus or minus half the smallest scale division, so that is plus or minus 1 millimeter. So 23.3 centimeters plus or minus a millimeter, so 23.3 plus or minus 0.1 centimeters. This is a slightly more precise ruler. It has a smaller resolution, and that's because its scale divisions are closer together, are smaller. So this is 32.35, I would say. And then we can read it to half the smallest scale division, and each one of these scale divisions is 1 millimeter, so it's plus or minus half a millimeter. So 32.35 centimeters plus or minus 0.05 centimeters. Average and spread. So we're going to put some numbers on things now. The mean value can be calculated using the formula that you know from GCSE. You add up all the readings and divide it by the number of readings. So this is you're reading measurements of variable x, and you've got the first time you measured it, the second time you measured it, the third time you measured it, and so on and so on and so on. So you add them all up and divide by the number that you've got. That's how you calculate the mean. And the random error, the uncertainty, can be estimated in two ways. Using the standard deviation, which is not needed at this level, but it's a better way of doing it. The way we're going to do it at this level is to use half the range of the values. So in formula terms, that would be the uncertainty, the absolute uncertainty, is the biggest of the values you measured minus the smallest of the values you measured divided by 2. And since we have two sources of error on a measurement that we can see straight off, we can see the resolution of the measurement, so plus or minus the smallest unit on a digital scale, or plus or minus half the smallest unit on an analog scale, and we've got this measurement of the spread. When we quote the absolute uncertainty, we're going to say either of those two things, whichever is the biggest one. And usually it's going to be the spread, the half the range. Significant figures for uncertainties. Absolute uncertainties are always rounded to 1 sig fig, certainly at this level. And the reason for that is because all of these things are estimates of the uncertainty. It is possible to get more significant figures in an uncertainty, but not with the ways we're going to be doing it at this level. You've got to wait till degree in order to get more accurate statistical measurements. So we're going to round our absolute uncertainties to 1 sig fig because that's all we're confident of. percentage and fractional uncertainties we usually keep to 2 significant figures as guard digits against rounding error. And that's because we tend to only use percentage and fractional uncertainties during a calculation. And then at the end, we'll turn it back into an absolute uncertainty. And the reason we want to turn it back into an absolute uncertainty is because of the way we quote our results. We quote our results to the same number of decimal places, not significant figures, decimal places, as the absolute uncertainty. So let's have an example. We're going to be measuring some time periods. And we measured a whole bunch of time periods. There they are. All of these are in seconds. And we can take an average. Now there are 10 measurements here, so the way you take an average is you add them all up and divide by 10. So this will give you an average of 1.2620 seconds. We're going to have a look at the spread. Now to do that, we're going to calculate half the range. Absolute uncertainty, therefore, is the biggest minus the smallest divided by 2. So that is 1.41, which is the biggest, minus that one, which is the smallest, 1.13, divided by 2. Now, we have an estimate of the value and an estimate of the absolute uncertainty. Now we put those together. This we round to one significant figure, so this would be plus or minus 0.1 seconds. And then we round the value to the same number of decimal places. So this is 1.3 to one decimal place, because this is to one decimal place. Error bars. An error bar is a way of drawing a value alongside its absolute uncertainty. We'll see this more when we come to drawing graphs, but it's useful for the next thing we want to talk about too. So here we have a value which is shown in the middle, and the bar reaches up to the value plus the uncertainty and down to value minus the uncertainty. So if we were to plot this on a graph, we would have this bar alongside the value. As an example, from before, 2.4 plus or minus 0.1 volts. The average value, the result of the experiment, is 2.4 volts. But the uncertainty says that the true value could be anywhere in here. So the largest value the true value could be is 2.5 volts, and the lowest it could be is 2.3 volts. Now this is very useful for the next bit. How do we know if an experiment is accurate? Well, we spoke about accuracy before. It's how close the measured value is to the true value. So an experiment is accurate if the measured value is close to the true value. Well, we only know that at the end of an experiment, once we've taken all the data and calculated it, and calculated our result and compared it to the end value. So we can only know if an experiment is accurate once we've compared the result it produced to the true known value. If the true value is contained by the error bar of the result, the experiment is accurate. This is because our experiment said the result is here, plus or minus a bit. If the true value falls within that, plus or minus a bit, then the experiment says that the true value is in this region and the true value is in that region, so it's accurate. So here is two different experiments measuring different things. This one measuring acceleration due to free fall on Earth, by the look of things, 9.81 meters per second squared is the true value, and our experiment gave us 9.7 plus or minus 0.3 meters per second squared. So if you were to plot this error bar, the true value is inside it. So this is an accurate result. This experiment said the true value is anywhere between 9.4 and 10 meters per second squared, and it is. This is accurate. This one looks like it's measuring the degrees C temperature of absolute zero, which as we know is minus 273 degrees C. our experiment says it's minus 275 plus or minus 1 degrees C. So that experiment says the true value should be anywhere in this region, and it isn't, so this is an inaccurate experiment. How do we know if two experiments agree? So we've got two different experiments measuring the same quantity. Let's say you and your mate both did an experiment where you were measuring acceleration due to gravity on Earth. And you want to know if you got the same answer. Well, there are ways of calculating how well two measurements agree with one another using clever statistical methods, but at this level it suffices to see if their error bars overlap. In an experiment, you're never going to get exactly the same result except by fluke. Because when you measure something multiple times, you'll have a range of different errors which have gone into the process and you'll end up with a different result from each other. How do you know if your results are compatible? Well, your error bars will overlap. The experiments here either do or don't agree. So these two have error bars. Now this experiment says the true value is anywhere between here and here. And this experiment says the true value is anywhere between here and here. And so there's this whole shaded region here where the true value could be, and for these two experiments to agree. Here there's an overlap of error bars, and here there isn't. So these two experiments agree, and these two don't. There are ways to say how much two experiments agree, but we aren't going to deal with that at this stage. All we need to be able to say is, do the error bars overlap? Yes, they do. In this case, so these two experiments agree, and they do not overlap in this case, so the experiments do not agree. And what I mean by that is this experiment says the true value is anywhere between here and here. And this experiment says the true value is anywhere between here and here. And those two don't agree, those two don't overlap.